All right, good afternoon, everyone. Hope you had a good weekend. Let's get started. Does anybody have any questions on the midterm this Friday? Okay, great. No questions. So let's finish up the classification unit that we were working on. We're almost done. So last time we were talking about the way that you measure performance for binary classification. And we wrote out this confusion matrix, which shows the 4 different possibilities of what can happen with the true label and the predicted label. And we noticed that there's 2 different ways to make an error. And in some applications, it's safe to treat those as equally bad. But in other applications, like we talked about cancer diagnosis, one of those might be a lot worse than the other, and so you don't want to treat them the same. And so accuracy is a metric where essentially you are treating those 2 errors the same in terms of importance. That's sort of the default metric, but like we said, that might not be what you want to do. So we have some other metrics like precision or recall. Both of those, so for example, in terms of interpretations, given a positive test, how often is the patient actually sick? Or given a sick patient, how often is the test correct? So on. We have interpretations for them. These would actually give you a pair of metrics, and if you had a pair, it wouldn't be really clear like what's better. If one is, precision is better and recall is worse, do you say that the method is better? So there is a way you can average them in terms of F1 score to reduce them to one specific number. And then we have similar things we can do, similar concepts in medicine like sensitivity and specificity. Okay, so this is one thing we talked about. These precision, recall, F1 score, accuracy are very easy to measure in sklearn. They're part of those default list of scores you can use. And then we discussed another sort of freedom you have. So when you train logistic regression, you are not training it to maximize accuracy or precision or recall or anything. You're just training it to minimize logistic loss. Okay, so it does not really care what you're interested in. But when you finish training it, as we know, you can compute these scores, you can compute these soft decisions, but eventually you may need to compute a hard decision. And at that point, that's where these metrics come in. That's where you're actually making errors and so on. So at that point, you do have the flexibility to use a different threshold than 0.5 on the confidence. So if you say my confidence is a soft decision that's between 0 and 1, if you threshold that at 0.5, that would be the right thing to do if you want to maximize accuracy. However, if you want to somehow balance precision and recall in a slightly different way, you can use a different threshold than 0.5. And when you do that, you can see if the threshold increases, precision goes up, which is good, recall goes down, which is bad. So here, it's not really clear maybe until you get into the details of the application exactly where you want to be in terms of the precision recall trade-off. So that's something that you need a lot more information to decide, but there's a way, once you know what you want to do, there's a way to deal with it just by changing that threshold. And there's something very similar here for sensitivity versus specificity. And then we saw one more very similar trade-off. This is between TPR versus FPR, true positive rate, false positive rate. So when you look at this, as the threshold increases, the true positive rate comes down, which is it's getting worse. But the false positive rate is also coming down, which means it's getting better. So as you move to the right, one gets worse, the other gets better. It's not exactly clear what you want to do. Maybe you need to know more about your application to decide that. But once again, you can choose T, the threshold, to navigate that trade-off. And this is a particularly important pair because people often plot these two quantities versus each other here in what's called the receiver operating characteristic, or ROC. And so here is just another visualization of this plot that we saw below, where you're plotting TPR versus FPR as you vary that threshold, and you can see you go to all those different trade-off points. Ideally, you would like to be here. It's not really clear which of these is closest to here in the right sense, but you can see you have several choices that you could make. So if you don't know exactly where you want to be on this trade-off curve, then what you can do as a way of measuring the overall performance is you just take the area under the curve, which is obviously something that increases as the curve gets closer and closer to that top left quadrant. And so this is a very popular way of measuring performance, different from accuracy, that's trying to get a different balance, yet is still threshold independent. It's probably the most popular one that I've seen. So, okay, and then we talked about how to do that in sklearn. Okay, so any questions on any of those concepts? Okay, so that's all for binary classification. Now let's think about what happens in multi-class classification. So in this case, our confusion matrix is a lot bigger. So if we have capital K classes, we have a K by K confusion matrix. So the terms along the diagonal here are measuring correct decisions. So like when the truth is 1 and you predict 1 and so on. All the counts off the diagonal are measuring errors, but there's many, many ways to make errors here. If you're given a confusion matrix like this that has just raw numbers in it, it's hard to interpret it. So what's more common is to normalize the rows so that they sum to 1. So for example, if we make all these values sum to 1, then we have a valid probability mass function, given that y is 1. Given that truth is 1, we see the PMF of the decisions. So that's a typical thing. So in that case, for example, the kth entry in the table becomes the probability the y hat is L given that the truth is K. And we also, in that normalized case, the diagonal terms give us our per class accuracies. So the accuracy if the truth is K for different K. And so this is a very common thing to do, is to normalize that confusion matrix. Okay, so as you can see now, there's going to be capital K different per class accuracies along the diagonals. And if you're interested to know what is the relationship between those per class accuracies and the overall accuracy, it's given by this equation here. So if you're familiar with conditional probabilities, you might immediately see that this must be the case, because when you multiply these two things here, you have probability y hat given y times probability y. Does anybody know what this is? In terms of probability, what is this? The joint probability, exactly. So together, this is the joint probability that y hat is K, comma, or and y is K. And then second step is if you take this joint probability and you sum over one of them, then by the law of total probability, that just removes that dependence in your okay, so yeah. So essentially what it does, it's essentially going to average over all those different cases. So this is how the overall accuracy relates to the per class accuracies, and it will be important when we talk about what happens when these guys here are not well balanced. We'll talk about that on the next slide. But so here's overall accuracy. This is probably the most common metric people use in this multi-class setting, although as we know, it may not be what you want to use if you care about some of these accuracies more than others. Now you might wonder, what about all these other metrics here like precision, recall, what do you do with those in the multi-class case? And so there's actually different things you can imagine doing here. But after looking into it, it seems like the most popular, most robust choice is if you want to do a multi-class precision, you use these what's called a micro-averaging of the K versus rest metrics. So let me first describe what is this K versus rest metric. So let me make a little table here. So this is going to be y equals k. Let's say the top y is not equal to k. And then we have y hat equal k, y hat not equal to k. So for example, if I'm focusing on k equals 1, then this would be what's there. This block would sum over all of these. This block would sum over all of these. And this block would sum over all of those. Okay, so these are the one versus, or K versus rest metrics. So we can give these names. We can call this the true probability sub K. Let's see, what do we have? Then we have, it's basically the same as this table. False probability K, false negative K, and true negative K. Okay. So depending on which value of K you're holding out here, all these numbers will change. Okay. But for any given K, you can compute those numbers. And then for precision, you use the precision formula that we saw on the previous page, except that you do a separate average over K in both the numerator and denominator. And it's a similar thing for recall. And if you want to compute the true probability and false probability rates, then you can again use those K versus rest metrics in this way. So these are nice ways to generalize these different definitions for multi-class classification. Okay. Any questions? Let me just put a little arrow here. Are there any questions on anything here? Performance for multi-class? Okay, so just have one more topic to talk about then, which is imbalanced class labels. So what we mean by this is a case where some classes have many fewer samples than others. Or probabilistically, you would say, in the multi-class case, the probability that you get, probability of y being in a particular class K is much less than 1 over the total number of classes K for 1 or more K. So let's just talk about the simplest binary case. Let's say you're doing something like COVID testing. And let's say your population you're testing is 99% healthy, 1% sick. So think about that case. If somebody told you that they had a 99% accurate test, should you be impressed? What's an easy way to get a 99% accurate test when your population is 99% healthy and 1% sick? Say everyone is healthy, exactly. So you have a trivial test that always predicts healthy, and it's true 99% of the time. Obviously, it's trivial, it's useless. So you don't want to get fooled by high accuracies, especially in the case that you have imbalanced labels. So this is a serious problem in practice because it's actually something that shows up a lot. And so, there's a few different things we can do about it. So where this problem is coming from, this problem I just described in the binary case, you can kind of think about it according to this equation that we saw on the previous page. So this is the case where I said, one of these is 0.99, the other is 0.01. And if I want to get 99% here, then what I could do is I can make a trivial classifier that sets this probability y equals k, 100% chance it does this for my majority class, 0% for my minority class. And the reason why this is failing is that this guy is assigning all the weight to the majority class. So if you want, one simple way to try to get around this is what's known as balanced accuracy. And in balanced accuracy, you just throw away this term. You throw away that weighting term. So now you're just measuring, the sum of those kind of more raw conditional probabilities. And this is just one approach. It's not the only approach, but it is one thing that you can look at. Interestingly, another approach that some of you might be thinking of is, well, let's say I take my data set, that same data set where I have 1% unhealthy, and maybe what I could do is I could just copy and repeat that unhealthy, all the unhealthy samples, I just copy and repeat them 99 times. And so now I do have redundancy in my data set, but at least it's balanced. I have equal number of healthy and sick. And if you do that, and that's not a terrible idea actually to do that, you can do that, and what you would find is if you evaluate accuracy in that case, you would get the same thing as this. So it's just sort of a more direct way of doing that where you don't actually have to do any copy and replace. You can just measure that metric directly. Okay, so this is one thing you can do that might give you a more reasonable metric for this imbalanced case. Another thing you can do is you can look at metrics like the area under the curve of, this is the precision recall curve. So instead of the receiver operating characteristics, which is TPR versus FPR, this is precision versus recall, but it has a similar shape. And because we don't know exactly the threshold we want to use for precision and recall, what we can do is we can just look at the area under the curve, threshold independent, not have to make that choice. So these are probably some of the most popular ways to measure performance in this imbalanced setting. Yes?
Shouldn't there be 1 over k in balanced equation?
Yes. Well, actually, yes, there should. Yeah, thank you. There should be 1 over k. Otherwise, the number we're going to get is going to be too big. Sorry about that. So there should be a 1 over k here. Okay. All right. Okay. So that's one piece of the puzzle. The other thing that can happen is, as we said, when you train logistic regression, it doesn't really care about whether you're interested in accuracy or precision recall. It just minimizes logistic loss, which is nice because you don't actually need to make that choice for training. However, in this highly imbalanced setting, if you train and 99% of your samples are in one class and 1% is in this other class, you would find that when you minimize the logistic loss, you're looking at a sum of loss over your training samples, that this would be, again, highly imbalanced because most of your loss is coming from the one class versus the other. And that would cause even this logistic training to be probably suboptimal. It's going to focus too much on the typical case that happens, which is healthy patients. So scikit-learn gives you a pretty convenient way to deal with this. All their classifiers have an option called class weight. And if you set that option to balanced, then what it will do is, okay, I haven't read up on the documentation since last term, but I think what it does is it weights this loss so that whenever you have a sample from the minority class, I think it basically increases the value it uses in the sum. But the details are here if you want to read about it. And this is a nice way to make the training more robust to this class imbalance. Okay. Any questions there? Okay, and there's one more thing to think about, which is k-fold cross-validation. So again, let's say you're doing k-fold cross-validation, and let's say you're doing tenfold, k equals 10-fold cross-validation, and let's just say, for simplicity, that your data set has 90% majority samples, 10% minority samples. So in this case, what ideally would happen is every fold would have, 10%. Well, okay, all the folds in cross-validation would have that 10-90 split. Right. But that may not be happening in reality because the folds are randomly generated. So you could have some folds with a lot more minority samples, maybe other folds with no minority samples. And so when you start to do k-fold, the results are going to be a bit off. They're going to be more random than you'd like because there's this inconsistency due to the particular shuffle. So there's an approach to k-fold called stratified k-fold, which makes sure that all the folds have the same class balance as the overall data set does. It just forces that when it generates the indices for the splits. Okay, so that's another thing. So you have this stratified k-fold, balanced class weights when you do your training, and with these two things, you can make your classifier more robust to this presence of imbalanced class labels. Okay, so those are the main tricks people use. There are other things people have proposed, and you can find some vigorous debates online about what's the right thing to do, but I think this is sort of the most common practice here. All right, are there any questions on anything here? Okay, if not, I think that's all we have for this unit for classification. Though that's not going to be the last thing we say about classification, because we'll actually spend the whole few next units on it, but just different aspects of it. This is sort of the version 1.